Thanks for the introduction. Today, the topping model has been widely used for exploratory data analysis, but it is still largely unclear how do we achieve those topics due to the complex inference step. Recently, the anchor word method was proposed. So if we assume there's a specific word which is associated to each anchor, then the rest of the inference process becomes deterministic. However, it is still unclear how to interpret each topic because those anchor words are too eccentric. So two key ingredients of today's presentations are transparency and interpretability. This figure illustrates a user's view about topping model. So if we input documents, raw document in terms of words with the number of topics, then there's a certain magic black box which do the inference and outputting topics in terms of words and documents in terms of topics. And this process is not transparent due to this magic black box and hard to interpret. Our algorithm, which is called anchor word algorithm, there's an assumption. Every topic has an anchor, which is a specific marker associated with each topic. So the main three steps are, first of all, we build a co-occurrence, and then find anchor based on that co-occurrence statistics, and then we infer topics based on those anchors. See this figure. So this figure illustrates all co-occurrence patterns and their dynamics. The data set was from Yelp academic review data. And if you see the points and the vertices, those are the most distinctive vertices. And the key observation here is all the rest of the words in the interior points could be regenerated by the linear combination of those vertices. And here we are illustrating three different topics from three different data sets. The first topic from Yelp, it is about beer based on the words like pizza, wings, tap. And the second topic is about Islamic religion based on the word Allah, Muhammad. And third topic is clearly about stock market. And the anchor words are currently bold-faced as a red color. And as you could see in this table, anchor word separates topics and being exclusively dedicated only to that topic. This is the role of anchor word and makes the inference process transparent. And here we have three different topics. The way that we generated this table is we first pick one topic based on our TSNE model. And then we pick two topics from other model. One is another baseline method, PCA, and the baseline is from the previous work. So those two topics are selected as the most similar topic to our TSNE topic. The TSNE topic you've already seen, which is about beer, and the second topic is about wine. Even if there's a word beer in the second position, the rest of key contributing words are more about like leads to glass wines. But see the third topic, it mixes both beer and wine, but the rest of the words are pretty popular term, which is not that meaningful. And if you see the anchor word, it is indeed craft. I guess the reason why the baseline model picked this as an anchor word is there's terminology, for example, craft beer, but still the craft is not that meaningful to interpret this topic. And this is another example. And so our topic from TSNE model tells about the price aspect of restaurant review associated with service and quality. And another topic achieved by PCA model is talking about atmosphere or ambience aspect of the restaurant. But see the third topic. If you see top words, good, great, food, place, are you able to guess what the corresponding anchor is? It's Korean. I'm indeed Korean, but it's very hard to associate why this anchor is especially picked for this topic. So the current algorithm, even if it is transparent, still hard to interpret the topic based on that anchor. But our algorithm, anchor words are more understandable and contribute the most. That's the key ingredient for interpretability. So I'm going to explain two models, LDA and its first-order factorization view, and then anchor word and its second-order factorization view. This is a very popular graphical model for traditional LDA. So everything exists individually, like one topic and one topic for one word, and both process mixture of topic for each document or mixture of words for each topic are generated stochastically. So if I reinterpret this process in terms of matrix factorization, the M matrix in the right-hand side is term document matrix, whose column is about documents, whose rows are about the words. And we have topic matrix in the left-hand side, capital Phi. And currently we have 8 words and 4 topics. So if the first document is entirely about topic 1, we expect to see the first document contains the word 1, 4, 5. And if the second document is entirely about topic 2 and topic 4, we expect to see the words coming from the second column and the fourth column of the topic matrix. This is another view to interpret LDA. This is corresponding graphical model for anchor word algorithm. Notably, everything exists pairwisely. We sample pair of topics and we sample pair of words based on that topic. And only sampling the pair of topic part is stochastic, and generating topics in terms of word mixture is no longer stochastic. And it induces strong conditional independence, which means W1 is conditional independent to W2 given either of topic Z1 or Z2. So based on that model, our goal is to factorize our word-word co-occurrence matrix Q, which is in right-hand side, into 3 different chunks, A, R, A, T. A is same topic matrix corresponding to word given topic, and R models the joint distribution between topics. So recall the anchor word assumption. Every topic has a specific anchor word which is dedicating exclusively to that topic. I currently make those anchor word red. So we could identify 3 different rows where only one entry is activated. And if I correctly permute those rows so that it's going to be on top of the matrix to the top of the matrix, then it will look like this. And it means if we have anchor word assumption, then our topic matrix A has a diagonal matrix like this. And note that the matrix Q is also properly permuted with respect to A's permutation. So merging those R and A transpose part into one single chunk, then it's easier to view as a non-negative matrix factorization because we are having only 2 different chunks of matrix. And see this. So this figure illustrates the first rows of our observation Q is indeed replication of the first row of RA transpose matrix with respect to the scalar in the first diagonal entries given in A. And similarly, the second row of our observation is multiplication of the second row of RA transpose with respect to that diagonal entries in A. And similarly, third row. And see the fourth row. Because of matrix multiplication, the fourth row is a linear combination of first row and third row of RA transpose with respect to those two weight vectors in A matrix. And similarly, this is for the fifth row. And this figure means the first rows is in Q are the essential, and the rest of the two rows in Q could be reproducible as a linear combination of the first three rows, which are corresponding to anchor words. So I will briefly introduce about our inference process. Because of the illustration that we've seen, finding anchor words is equivalent to detect near basis row, and that is the most crucial part of this inference, because the rest of the process are entirely deterministic once we find these anchor words. So there are two different previous work. One is Aurora et al. 2012. They keep eliminating all the reproducible word row vectors by solving LP, but solving LP is very expensive and impractical. And next work, Aurora et al. 2013, they utilize Gram-Schmidt process by keep picking the farthest point and project every other points into the orthogonal complement of the current linear space. And by repeating that until we find k different points, they chose those anchors. But the problem is Q is gigantic. Let's say the number of words are 10,000 is 10,000, then Q will be 10,000 by 10,000 matrix. So projection is inevitable to play with. And the selected anchor words, as you already briefly seen in the introduction slide, it's too eccentric. So they utilize random projection, projecting everything down to 1,000 dimension. We are going to use T-SNE projection, which is T-stochastic neighborhood embedding method. And the projection dimension is extremely low, to 2 to 5. They approximately find those convexal in the co-occurrence pattern. Instead, we are going to find exact convexal because we are in very low dimension. It's easy to find exact convexal. The property of random projection is to preserve distance between the entities based on Johnson-Linden-Strauss lemma. The property of T-SNE is to approximate the local structure. And based on this, we are going to achieve visualizable and interpretable quality. So briefly, what the T-SNE does is it is a nonlinear dimensionality reduction scheme mapping the old representation X to the new representation Y. First of all, we define distributions on old representation and new representation, and the goal is to minimize those distributions. Because we are defining and minimizing those distributional distance, it preserves the local structure, and especially for the Q distribution, it uses heavy-tailed T distribution in order to avoid crowding problem. You're going to see what's the crowding problem in the next figure. And by doing this projection, we achieve more succinct summarization by less eccentric term. Experimental result. So the first figure shows T-SNE versus PCA. So T-SNE is our main model, and PCA is another baseline which we tried for this work. So as you could see in this figure, PCA also achieved general term in their vertices, but it's extremely crowded into one specific vertices, whereas our T-SNE model spread it out and it correctly better model for all the co-occurrence interaction. And this figure illustrates two-dimension versus three-dimensional projection. there is one interesting property here. So if we increase the dimensionality to project down, then we could discover more vertices like this. So, I mean, tuning the level of tuning the dimension of projection could be a way to explore a different number of topics. And see this table. So it illustrates the baseline anchors at the first column and the anchors coming from t-SNE model in the third column. So the anchors from the baseline models are either very centric or possibly typo, whereas our anchors are more general. So the first metric that I'm going to show is saliency. It measures whether the anchors are distinctive and frequent, because anchors by definition distinctive. What does it really matter is whether or not it's frequent. So the y-axis in the plot is measuring how far the anchor word is likely from the most prominent word. So the lower value is better. And as you could see, t-SNE is much lower than the greedy, which is a baseline method. And held out probability is a traditional measure which evaluates whether our topics could explain the unseen test data. As you could see in the plot for 3 different real data sets, our t-SNE method beats the baseline method by a margin. And recovery error. This explains how well our anchor words could summarize the rest of the word. So as you already see in the first slide, the key component of this inference is anchor word will play a role of basis, which could regenerate every other words. And this measure evaluates how well the summarization goes. And our t-SNE model works as comparable as greedy baseline, and if you see carefully, it's actually slightly better. And there are 3 different measures: specificity, dissimilarity, and coherence. And for this slide, I'm explaining only about New York Times data set. So specificity measures how far our topic from the corpus distribution. So if the number of topics is not enough or the inference is inferior somehow, then topics is likely to imitate the corpus distribution. That's why we are measuring specificity. And dissimilarity is how far each topics to each other. And coherence, this measure how likely 2 keywords in the topics will coexist in our training sample. So our t-SNE method and also PCA makes more specific and dissimilar topics, whereas coherence is a little bit lower, but still comparable around 90 topics. But see, PCA's topics are far less coherent. So the conclusion is, by mapping our co-occurrence statistics into extremely low dimensional space based on t-SNE, we achieve visualizable dynamics like this, and it makes all the inference process transparent in the sense that we now know why we achieve each of these topics, which is associated to anchor word. And that topic is now understandable and interpretable because we got an understandable anchor word which contribute the most to each topic. Thanks.
So I found that with the anchor method, the most important predictor of whether the model will be coherent or not is the vocabulary threshold. And so making that fairly high leads to more interpretable topics. So could you talk a little bit about how you selected your vocabulary cutoff? So you listed numbers for the data sets in the paper, but you didn't say how you got that.
Yep. So after sorting every vocabulary, every word in each data set in terms of the frequency, we cut out extremely high frequency words, which are corresponding to stop words, and we also cut out extremely rare word to be selected as anchor word. For example, if a word appears less than 3 times across all different tests, a training sample, then we explicitly prohibit those words from being selected as an anchor word.
Right, but how did you choose that number?
It's empirically.
Okay, so you held out grid search?
Yeah.
And okay, thank you.
More questions?
Okay, so your method relies on this notion of anchor word separability. So I'm wondering how can we know whether this assumption holds in our data? Of course, you use the assumption to learn topic model, but perhaps by using data sets where annotated topics are available, can we check how much that hypothesis holds?
That's interesting future direction. So if there's a data set available with annotation, what would be the correct topic based on human validation, then the anchor word, what we found and what was given from the previous method, validating those will be very interesting future direction.
We still have time for questions. Okay, we'll follow up then. So a more open question. So here you are detecting topics which can be interpreted as some sort of word clustering in the sense that each word is associated also with a set of topics, a soft word clustering, let's say, by means of comparing them across documents. So sometimes word clustering is in NLP is done by identifying a document with the context in which a word appears. So that gives us context-based word clustering, okay, which are useful for many applications. So to which extent this anchor word assumption and method could be applied to doing some sort of topic modeling of context in order to get a word clustering style of model.
So you want to utilize this anchor word model to infer underlying context of given documents?
So our documents would be just a window in which a word appears, such that I want to compress, say, context, and by that making a soft clustering of words. To which extent that would be possible?
I don't have a perfect answer for that, but we could utilize this method for many different data sets. For example, instead of using text document, we could do this exactly same process for a playlist in which song will correspond to the word. And yeah, if you define context as, for example, some hidden genre, which is underlying under all different playlists, then yeah, that is true.
Okay, let's thank the speaker again.